So thank you everyone for joining us today on the first of a series of 4 webinars around PFAS. Today's webinar will focus on new techniques to improve PFAS site characterization and conceptual models. My name's Martin Drager. I'm with Water Services and Technologies, and presenting today is Dr. Grant Carey, President of Pour Water Solutions. Grant's a recognized expert in PFAS investigation and risk assessment, and has more than 30 years of experience with remediation of hundreds of impacted sites. Grant's currently involved in 7 SURDIP and ESTCP projects for the U.S. Department of Defense, with focus on PFAS in situ remediation and modeling and visualization. Grant's also an adjunct professor, a research professor at Carleton University and in Ottawa, and an adjunct professor at the University of Toronto. So before we go into the webinar itself, I'll just go through the agenda. We have about an hour, just less than an hour of reserved time. We will have questions at the end of the webinar. So if you have an idea question throughout, please feel free to post your question in the Zoom window and we'll get to it at the end of the presentation. If we don't get to your question, we will be sure to email you directly the answer. Also, we'll go a little bit about who Water Services and Technology is, why we're interested, and why we've joined with Grant in this webinar series. We'll also go through, Grant will take over and go through the overview of PFAS site characterization and run through some visualization case studies for the South Dakota Air Force Base, Michigan Air Force Base, and also the Michigan landfill site. And then Grant will end the webinar with a hands-on visual PFAS demonstration. So a little bit about Water Services and Technologies and our interest in working with Grant. So first, you may not be aware, our founder, Nilsen Giger, started this company in 2017, and we are a service provider. We provide environmental consulting services and a lot of environmental data management services to a variety of sectors. In mining is our primary sector of focus, but we do offer services to private and public sectors in water resources, water and sanitation, industrial and energy. Now, we do offer an immense amount of data management services, and with this particular webinar around PFAS, as you can imagine, there's a large amount of data that needs to be managed. So we have interest in helping those with the data management side of things. In addition, we do offer products and training services to most of our clients so they can carry on with their business in a productive manner. And as part of that portfolio of products, we've just introduced Visual PFAS, which you'll learn a little more about in this particular webinar. So we actually have our president CEO who started the company. You may be aware of the product called Visual ModFlow. He developed that globally, is distributed, and we also have FlowPath, had developed FlowPath 2 at the time. And so we are really in our culture embedded in technology. So we're really excited to present this new technology on PFAS. And Grant, go ahead. The floor is all yours.
All right. Thanks, Martin. Hello, everyone. Thanks for joining today. We really appreciate your time and coming out. Before I forget, if anybody wants a copy of the slides from this presentation, feel free to send me an email at any time. I'm happy to forward them to you after we're done here. So as Martin had mentioned, I'm really fortunate to actually be involved right now with 7 different SURDIP and ESTCP projects, mainly with modeling PFAS in situ remediation using in situ barriers, absorption barriers. So as part of that, we're getting a lot of data from different field sites where these barriers have been installed and pilot tests. And I've had to really wrestle with a lot of PFAS data and trying to better understand, what's happening, upgrading of the barriers, in the barriers. And that's where we got more into the visualization side of things and why we came up with Visual PFAS, just as a way to try and better understand PFAS data at these sites, because we just collect so much of this. So just to give you a quick example of how we're visualizing remediation performance with absorption barriers. So some of you may not be aware. I think a lot of you probably are. Plume Stop is one product that is it's colloidal activated carbon, or CAC. It's like these tiny little particles of activated carbon that are injected in the ground through temporary injection wells, and this carbon will actually attach to sand grains within a barrier footprint in an aquifer. So in this cross section that we're looking at, the red plume is PFAS coming into the barrier, the up-gradient side. PFAS absorb really strongly to activated carbon. So the PFAS will absorb, essentially get filtered out of the groundwater, and we'll have clean groundwater leaving the down-gradient end of the barrier. So just to show you an example of what that looks like, there's a field site I'm working on with a few other folks. And this is a radial diagram, and there's 5 axes. We've got sulfonates on this diagram, starting with PFBS on the left, which is the shortest chain sulfonate in the diagram. And if you go clockwise around that radial diagram, you'll see that the chain lengths are increasing as we come up to PFAS on the bottom. And the red data series, that represents pre-injection concentrations. The green data series, those are the concentrations measured at a monitoring well in the barrier 3 months after the barrier had been installed. And if you look at the PFAS axis, just as an example, you'll see that between pre-injection and post-injection, concentrations drop by 3.5 orders of magnitude. And we can see 4 of the 5 PFAS constituents are non-detect at that well, which is great. That's what we want to see. A lot of non-detects, a lot of big drops in concentration. And then looking at a radial diagram for carboxylates. These absorb a little bit less than sulfonates. And we see PFOA, similar to PFAS, 3.5 orders of magnitude decline after the barrier was installed, which is great. And then we've got PFBA and PFPEA. They're the 2 shortest chain carboxylates here. And we can see they haven't declined that much. They actually declined, and then they're kind of coming back shortly after the barrier was installed, which isn't surprising because these short chain carboxylates absorb the least of all these compounds to activated carbon. But it's actually okay because in this particular state, these short chain compounds aren't regulated. Usually it's the long chain compounds, PFOS, PFOA, maybe PFHXS, PFNA. Those tend to be the ones that are regulated with MCLs or with state-specific criteria. So that's just one example of how we can take these 10 PFAS constituents, 2 different monitored events, and very simply show what the data look like before and after injection. So that's where visualization can help us much more so than if I showed you a table of data and asked you to kind of figure out for yourself what was happening. So with site characterization, I'm sure a lot of you are familiar with the fact that at any site where we're collecting PFAS samples, we're now getting up to 40 analytes coming back from the lab with results for each sample. Sometimes we might need to look at if there's co-occurring chemicals like chlorinated solvents, hydrocarbons. They may affect remediation. Maybe they need co-remediation. And then redox indicators. Redox zones are important because with PFAS, there are some PFAS precursors that can actually biodegrade to the PFAS of concern and cause an increase in concentrations of those PFAS of concern. And that tends to occur mainly under aerobic conditions. So sometimes if we're a little bit worried, we might have precursors naturally biodegrading, causing higher concentrations of regulated PFAS. We might need to look at redox indicators as well to evaluate where that may occur at a site. So the conventional way of looking at PFAS up until just a few years ago was really, I call these box table plots. We basically take these data, we put them into tables and then draw lines connecting the tables to the well locations. It's a convenient way to summarize the data on a figure. But if you think about it, if you kind of step back and look at this and just ask yourself, where are concentrations the highest and where are they the lowest? It's not something you can evaluate immediately. You have to look at every box in this figure to figure that out. So that's not what I would call a visualization method that helps us quickly see how things change across the site. So that leads to the question, how can we effectively communicate all the results that we're getting at these PFAS sites? And when we think about how are we going to communicate all this, how are we going to evaluate it, we have to think about what are the things we actually need to look at. And on top of looking at, say, individual species and where they have exceedances, a lot of well locations, a lot of plumes, we need to look at interrelationships of multiple PFAS at the same well location. And then we have to evaluate how those relationships change as a plume moves down gradient of a source area. So it's not just looking at one PFAS at a time. So sometimes we might have a number of PFAS that are of concern that we might want to show exceedances for on a single map. Like we talked about with remediation, we might want to know how much PFAS are short versus long chain. That may actually affect what remedies are feasible at a site. If we're looking at precursor degradation, we have to look at the parent species and the daughter products together. Plume attenuation, site versus background, top assay results, remediation monitoring, source forensics. All of these different things we might have to do with site characterization. They all involve looking at multiple PFAS at the same time on the same map, ideally. So the good news is there are some methods available that make that pretty easy to do. There's radial diagram maps that we saw earlier as an example, and stack bar maps. And everybody's used stack bar maps or seen stack bar maps used in Excel, where we'll have stack bar charts, a number of bars side by side, but not on a map. And last summer, we started working with one Air Force base, the South Dakota site I'll talk about in a minute. And I found looking at actually mapping the stack bars really added a whole new dimension of being able to look at spatial analysis or spatial trends that really open things up in terms of fingerprinting what's in different source areas and things like that. So I'll show some examples in a few minutes of that. And radial diagrams aren't new either. I mean, these have been around for decades, really, many decades. PFAS is a kind of a new application, just because there are so many different PFAS we have to look at. Radial diagrams just make it pretty simple to plot multiple chemicals on a single map. So I was involved back 2017 to 2020 on the ITRC PFAS guidance team. And one of the things I contributed was actually some case studies looking at application of radial diagrams for characterizing PFAS sites. So, and just to show you an example, this is a recent journal paper from 2023. We can see these are two radial diagrams representing conditions for a single well. So the one on the top, those are the carboxylates like PFOA. Those axes go up to 60 nanogram per liter. And then the sulfonates on the bottom, those go up to 140. So it's not bad, but when you look at it, like I've seen these plots quite a bit in presentations, not usually on maps, but usually presentations for single well trends. And if one thing I find difficult is, for example, if you look at the green data series on the bottom, which is post-remediation concentrations measured at a well, and if you look at the PFAS axis and you look at the concentration, to figure out the concentration, you have to kind of line it up with the one axis that's labeled, which makes it about 80 nanogram per liter, but that takes time to do. So it's not very easy to read the concentrations from that kind of a plot. What I tend to do is I might actually join both of those into a single radial diagram, and you can see on the top axes, those are the sulfonates, and the bottom axes, those are carboxylates. And on the left side, this is what I do pretty frequently, is I put the long chains on the left side and the short chains on the right side. And that helps us look at trends for sulfonates versus carboxylates, short versus long chains. And you can see each axis actually has its own labels. We have sulfonates going up to 200 nanogram per liter, carboxylates up to 60 on each axis. So by actually putting them all on one axis or one radial diagram, it just makes it easier to look at the overall trends. So simple improvements that actually make a big difference, I think, are just actually combining these so we're showing different ranges for different chemicals. Sometimes we need to do that. Actually showing all the axes lines, labels on all the axes, not for maps, but just for looking at individual wells. And then adding the symbols. I find that can make a big difference with showing where we have exceedances for certain chemicals and where we have non-detects and where we don't have non-detects. So what I'm going to do is first walk through this South Dakota Air Force Base case study to show you both radial diagram and stack bar examples. I have worked with a group. We've got a paper in press now with Remediation Journal. Anybody that would like a copy, I'm happy to send you the kind of draft, the final draft that we have. Just send me a quick email and I'll forward you that paper with all the figures. There's lots of figures, lots more than I'm going to show today. And I do want to have a call out to my co-authors on this. Rita Krebs is with the Air Force Civil Engineer Center. She's actually the RPM for this site. Was super helpful in terms of helping me understand what's happening at this site and sharing the data with us. Jeremiah Duncan with GZA Gabe Carey, who's actually the developer of Visual PFAS, and helped me to actually develop tools that really helped us specifically with this site. This is a study we looked at last summer. And then also Mia, Jillian, and Kira from Pure Water Solutions as well were very helpful. So one thing we try to do with this site, just as an example of can we do it, or a question, I wanted to try and figure out, can we use visual methods to actually figure out what were the predominant AFFF products used in the different source areas at the site? Can we actually see where they're distinguishable? So we've got a little over a dozen source areas, known source areas. AFFF1 in the bottom is where the current fire training area is. And OU1 is the former fire training area that was used until about 1990. They stopped using it then. They created the new fire training area that was lined with concrete. And we've got all these other places. Some are crash sites, some are buildings where PFAS were stored, etc. So in terms of AFFF products, there's really two manufacturing processes that result in very different signatures in soil and groundwater. The first process we'll call electrochemical fluorination, or ECF. And AFFF products, this is AFFF, it's aqueous film forming foam. It was used, that's the foam used in fire training at not just military airport sites, a lot of civilian airport sites, municipal fire training as well. So one type of product was produced with this ECF process. And when we see soil and groundwater impacts from that product getting into the ground, we tend to see high sulfonates like PFAS and PFHXS and lower concentrations of carboxylates. The second process is called fluorotelomerization, or FT. And there's really two categories of FT products. There's the legacy FT products, which tend to have more long chain compounds in them. And then there's the modern FT products, where short chains replace the long chains. So they're much more dominated by short chain PFAS. So we tend to see with FT products, when those get into the ground, we tend to see soil and groundwater impacts with high fluorotelomere sulfonates, particularly 6,2-FTS at a lot of sites. We also tend to see high carboxylates like PFOA, for example. And we see lower sulfonates like PFAS. Sometimes we've got both products used in the source area, and you see kind of a mix of these trends. But now we've got clues. Looking at the two different types of products and the three categories here, two things we can look at are, is in any source area, we can look at what's the ratio of sulfonate to carboxylate concentrations. And to better understand, is it legacy FT or modern FT, we can look at long chain versus short chain carboxylates. So this is kind of these are the forensic clues we're looking for in the different source areas. So in terms of PFAS radial diagrams, I've got a couple things I typically do with PFAS, also with chlorinated solvents. This is a simple radial diagram we're looking at now. On the left axis, that's a precursor, FHXSA, that can biodegrade to PFHXS, typically under aerobic conditions when it occurs. And we've also got on the top axis PFBS, bottom axis PFAS. And the data series we're looking at in blue, that's the monitoring event results from 2011 for this South Dakota site at this one particular well, GW4. Now, what I do is I actually like to plot at least two series on each radial diagram map that I'm using. And I actually look more at the gap between the series than looking at the well data series on its own. So the second type of series we can plot is what I call a reference series. And that reference series, in this case, these are the maximum concentrations from the source area upgrading of this well. GW4 is about 400 or 500 feet down gradient from the source area. And we can see, if you look at PFAS, for example, the well concentrations at GW4 in blue are close to 2 orders of magnitude lower than the source concentrations that are upgrading of this well. So the precursor is about an order of magnitude less at GW4 than the source, and same with the other two PFAS compounds. So one of the things I talked about plotting, which I find there's no cost to this, it doesn't take up extra space, is plotting these symbols. So where do we have exceedances of each of the chemicals on the axes? And then where do we have detect or non-detects? So especially with remediation, you'll like to see a lot of non-detects. So plotting the symbols for non-detects can actually, these give us another layer of information that's no cost, doesn't take up extra space on the map, but provides valuable information. So at this particular site, before they really knew that PFAS were there, they actually had implemented a remedy for hydrocarbons, which involved infusion of dissolved oxygen through injection wells into the aquifer. The reason for that was they wanted to degrade the hydrocarbons aerobically through aerobic biodegradation. But remember how I mentioned before, precursors that can degrade to PFAS of concern, like PFHXS, they tend to degrade more often than not aerobically. So if we're injecting oxygen, that could really stimulate precursor degradation and cause increasing concentrations of the daughter products like PFHXS in this case. And just a side note, that's the same thing with chemical oxidation. If you have precursors present, chemical oxidation will also stimulate the precursor degradation to potentially PFAS of concern. So you have to be very careful with that. So this process of the dissolved oxygen infusion causing precursor degradation was well noted in McGuire et al. From 2014. Excellent paper. And just to show you a downgradient well as an example, we can see the precursor is dropped orders of magnitude and concentration, downgradient of where that dissolved oxygen infusion well is located, and it's now non-detect, which we can tell by the symbol. And you can see PFHXS is increased by about an order of magnitude at the downgradient well. And same with PFBS and PFAS, they also increased, which means we probably had some other precursors there biodegrading because of the dissolved oxygen infusion. So very easy to show this with radial diagrams where we're looking at both the parent species and the daughter products on the same map. Okay, so now let's go back to the site-wide look. This is a 5,000-acre facility, the South Dakota Air Force Base. We're going to look at each of the source zones and specifically for each source area, the maximum concentrations within each source area. And we can see in the radial diagrams here, I've got the sulfonates on the top axes. I've got the carboxylates on the bottom up to PFNA. We've got the longer chain compounds on the left side and the short chain compounds on the right side. And that just helps us look visually to see where we have changes between those different types of chemicals. So now plotting these on a map, we can see that, for example, remember how before I said we want to be able to see where we have the highest concentrations? Well, you can see right away it's AFFF1. That's the current fire training area. And you can see AFFF8 down at the bottom. That's got a lot of non-detect symbols. So clearly those are the lowest concentrations. That's a former crash site where it doesn't look like there's much in the way of AFFF impacts today. And then if you look at the top of this map, AFFF12 is near the top of the source, this one source area at the top. And looking at that, you can see on the left side, the long chain compounds tend to be lower concentration than the right side, which are the short chain. So long chains are less than short chains. We have both sulfonates and carboxylates present. We can see that between the top and bottom axes. So that's where having long chains and short chains on two different sides of the diagrams and your carboxylates and sulfonates on top and bottom really helps us evaluate pretty quickly where we have similarities and differences between source areas. So moving now, let's look at stack bars, it's all about proportions with stack bars. We're not looking at magnitudes of concentrations. And this simple stack bar is just very quickly telling us what's the relative concentrations of the sulfonates, the PFSAs, to the carboxylates. So we can see out of the sum of those two categories, the sulfonates represent about 70% of the total at this particular source area, and the carboxylates are about 30%. And we know, just looking at the tick marks, we can measure what the differences are. So now when we go and put those on a map, one thing I find really useful is putting the tick marks for the stack bars actually on the map. So if you look at AFFF1, for example, I can see that the orange, the sulfonates, are a little over 60% of the total for these two categories. Carboxylates are a little less than 40%. So having those tick marks makes it really simple to try and estimate the proportions of the different areas. And now if you look at AFFF6, which is a little bit to the right, total PFAS concentrations of 3.1, that's what's in brackets, 3.1 microgram per liter. And we can see the total carboxylates at AFFF6, much more blue, that's close to 80%. So very different from AFFF1. AFFF1 looks like it had mainly the ECF-based AFFF products released at the current fire training area, whereas AFFF6 obviously had a lot more of the fluorotelomere-based product released. And then AFFF12 at the top, that's the one we looked at earlier, that's got about 60% carboxylate. So a little more FT products released there than ECF, but it looks like both were actually released in that area. And then looking only at the question where FT products were released, what was the ratio between modern, which is mainly short chain, and the legacy, which is mainly long chain? If you look at the current fire training area, AFFF1, we see it's 80% short chain products, which means current fire training operations looks like they've mainly had the more modern FT released. And AFFF12 is 95% short chain, which means that's almost all modern AFFF products that were used there. So you can see how this very quickly lets us look at proportions, which helps us evaluate maybe you have multiple sources or multiple sites contributing to a commingled plume. If they have very different signatures, that's really simple to show with stack bars on a map, just as an example. And then, so a lot of you will probably realize, or probably have realized already, stack bars are actually the same as plotting pie charts. Both show proportions. I find just intuitively, I actually like the stack bars a bit better because we're going from short chains at the bottom to long chains at the top. It's just a linear progression. Whereas the pie charts, you're starting with a circle. You have to know where the circle starts. And I find estimating the proportions are really simple to do with stack bars using the tick marks. Whereas the pie charts, we don't have that. Like it's harder to estimate other than maybe if it's 50%, that's easy to tell. If it's 15%, that's just a harder thing to estimate with pie charts. So a few advantages with the stack bars, but they're purpose-wise, they're kind of the same thing as pie charts. Okay, so at this site, we really wanted a way to evaluate how do we actually evaluate or see if there's evidence of transformation from a precursor like 6,2-FTS to the daughter products. And 6,2-FTS, it actually has branch decay pathways. It'll decay mainly to PFHXA and PFPEA, the longer chain compounds of the three here, and it degrades less to PFBA, that's the shortest chain. So what we did is we said, okay, let's look at ratios and see if ratios rather than concentrations on radial diagrams can actually help us see evidence of transformation. So plotting this on a radial diagram, we've got three axes, and you see they all three axes have the same precursor on the top of the ratio. That's the parent species 6,2-FTS. And the daughter products are all on the bottom of the ratio. And if you think about it, if 6,2-FTS is biodegrading, that's the parent species. If it's biodegrading, its concentrations are decreasing along a flow path. And if the daughter products are increasing, both those things mean that the ratio will decrease along a flow path when this transformation is occurring. And we can see in the source area, the ratio is typically about 1 for all three of these axes. And yet at the downgradient well, downgradient of where oxygen was injected, we can see the ratios, like for example, the PFHXA ratios drop by more than an order of magnitude. A little bit smaller decline at PFPEA, and then the smallest decline of PFBA. So that shows that that's actually really good evidence that the 6,2-FTS has been biodegrading along the flow path, probably stimulated by the injection of oxygen. And that's shown by both 6,2-FTS decline and daughter product increase. But now we're using ratios to actually show that instead of the actual concentrations. So it turned out to be a nice, simple way to actually visualize that. Okay, so I'm going to go through 2 more case studies, and then we'll look at a hands-on demonstration with the software so you can see how it's used to actually create figures like this. So this next Air Force Base is actually Wurtsmith Air Force Base, just using information that's publicly available on the internet. I haven't worked on this at this site. And we're looking at the former fire training area, FTO2, and a downgrading area in terms of groundwater pathway. We see some green symbols where they collected pore water and some orange symbols where they collected surface water samples. So we're going to look at that in a little bit more detail. And one thing I wanted to evaluate with these data are we seeing evidence that the PFAS that absorb more strongly to organic carbon, are they actually showing preferential absorption in sediments where we typically have high organic matter concentrations? So PFAS, for example, absorbs more strongly than a lot of the other PFAS compounds. do we see it dropping out more quickly in the sediments between the groundwater concentrations of pore water or between pore water and surface water? So that's one of the things I wanted to look at with these data. So we can see we've actually got 6 pore water samples along the outside of this beaver dam. We've got 3 surface water samples downstream, and we've got one monitor well that was near this area with data. So this is what the table looks like. And I thought this expression, I saw this photograph, and I thought it was priceless, because this is what I feel like a lot of the time when I look at tables like this. I cannot tell you right away what's happening with the data. So that's a big reason why when we get these big data sets with remediation sites, I really like to use visualization to better understand it. So this is one radial diagram, just as an example. The outer data series, that's the highest PFAS concentrations out of any of the media, groundwater, pore water, surface water, from this area. And the blue data series, for this particular case, that's a pore water sample. So we're looking at the pore water results. We see both the maximum numbers and even the pore water sample. It's kind of elongated along that PFAS axis, because that tends to have the highest concentrations at a lot of the samples, and certainly the maximum at the site. So let's first look at, I'm going to look kind of at a progression of data in different slides. So first, we're simply looking at MW13, that's the groundwater well, and we're looking at concentrations from the shallowest screen at that well. I'll show you what the nested screens look like in a minute. So the shallowest concentrations are here, that's the blue data series. And then we've got one pore water sample that's closest to the groundwater well. And they actually look, if you look at them, they're pretty similar trends. The carboxylates look pretty similar. The PFAS and the PFHXS are about 3 times lower in pore water than they were in groundwater. Otherwise, everything's pretty similar. Maybe that's because of preferential absorption in the sediments, because of absorption to the organic matter. It's not really enough of a difference to say for sure, because this pore water sample is about 300 to 400 feet away from the groundwater well. Maybe it's just a difference in the groundwater concentrations discharging there. But interesting, at least, we do see some reduction in the sulfonates, which tend to absorb better than the carboxylates to organic carbon. And just a quick way to visualize, this is looking at a profile now. Ground surface at the top, the shallowest well screen is where we've got the highest PFAS concentrations at this nested well, MW13. We see the 2 middle screens, very low concentration, some non-detects in there. And then the deeper screen, things have gone up a little bit, but we can still see, just counting the tick marks between the top and the bottom screens, we can see that the bottom 34 to 35 feet, that's about an order of magnitude lower than what we have in the shallow zone. And that's not unusual to find the highest PFAS in the shallow part of the aquifer. We know that especially PFAS and longer chain compounds absorb pretty strongly to the air-water interface around that water table. So we might have higher concentrations in the shallow part, but we do have something that's gotten down deep, obviously, in the lower screen there. And then just looking now at stack bars, usually I try not to show too many chemicals on stack bars, but I wanted to try this. Remember with the last site, I showed 2 stack bar maps. One was only looking at ratio of total sulfonates to total carboxylates. The second map showed the short chain and long chain carboxylates only. I'm actually putting both of those together on this one stack bar map. I wanted to see how effective this might be in looking at trends. So we can see, just visually looking at it, MW13 and the pore water sample we saw with radial diagrams. We can see the PFHXS, that's the orange zone, that is higher in the groundwater well. PFAS is a little bit less in the pore water sample proportionally than in the groundwater well. Could be different, extra absorption of the PFAS, I'm not sure. And slightly higher carboxylates in the pore water sample compared to the groundwater sample. But now when we add in other pore water samples, we see a big difference. So you're looking at the pore water samples on the right side of the dam, the east side, they're all pretty similar, really heavily dominated by PFAS. And we've got some PFHXS, but low, and they're all low carboxylates, typically less than 20%, 10 to 20% for carboxylates. And then the one pore water sample up top, that's also different, almost no PFAS in there, but pretty high PFHXS. That's pretty unusual. Normally, you tend to see those 2 together. If you see low PFAS, maybe there's higher organic carbon in the sediments there and it's absorbed out, or maybe there's something in the sample. Maybe PFAS got absorbed to the air-water interface, not sure. But clearly you can see some differences here between these different samples. And then finally, looking at surface water, the surface water looks a lot like those four pore water samples with high PFAS, but it's a little bit less PFAS now at 60%. And I'm telling that by the tick marks, whereas the others are typically 80% PFAS or more. So maybe what's happening is we had high PFAS in a lot of the surface water in the dam, similar to the pore water samples. But as it moved through an area, maybe it's getting diluted with discharge from the south end, which looks like it has less PFAS. So that surface water might be kind of a mixture of both types of water. And as you go further downstream, we see PFAS getting to be less. Carboxylates are changing a little bit. That SW3D, maybe that's more affected by groundwater discharge with a different signature. I'm not sure. But it just shows how effective these stacked bar maps can be when you're actually trying to look for distinguishing between types of discharges, say, in this case. Okay, and finally, I'll just look at some redox zones. And this case study was actually from 30 years ago, if you can believe that. And I'm showing it today because with PFAS, redox zonation is actually really important. Because if you remember that the precursors that can degrade to the PFAS of concern that we don't want, they're the regulated compounds. So precursors may degrade to regulated PFAS, causing their concentrations to increase. And that tends to happen under aerobic conditions. So with radial diagrams, there's a special trick we can use unique to the Visual PFAS software, which really makes it obvious where we've got aerobic and anaerobic conditions. So at this particular case study, you see the gray drum area. That's an area where drums had been buried many decades ago. They were remediated, I'd say, late 80s, early 90s. It was recognized that there were some liquids released during the excavation process from the drums. The drums were in pretty bad shape. When we look down gradient, you see the down gradient of the drum area with the blue arrow. We've got two redox diagrams where the orange shapes are really small. And in the background area, that orange shape is really big. So I'll tell you what chemicals are on these axes in a minute, but I can just simply tell you where we've got a large orange shape, that represents aerobic conditions. Where you've got the really small orange shapes, that represents strongly anaerobic conditions. And the mid-size orange shapes are moderately anaerobic conditions. So I can quickly see we had background aerobic conditions in groundwater. Groundwater moved through the drum area, probably stimulated natural degradation of whatever organic chemicals had gotten into the aquifer. And we're seeing the effects of that with really strong anaerobic conditions, downgrading of the drum area. And downgrading of the rest of the municipal landfill, we've got moderately anaerobic conditions where, because of leachate vertical migration from this unlined landfill. So very quickly, we can see where we've got aerobic, strongly anaerobic, moderately anaerobic conditions. And again, if anybody wants a copy of this paper, by all means, send me an email. Happy to send it to you. And what we do is just plotting redox indicators. Oxygen, nitrate, iron and manganese, sulfate, methane's typically plotted. So just to show you the redox diagram in the bottom right, you can see at a well, we might have strongly anaerobic conditions, and we've got aerobic conditions in the background well. And if you just look at nitrate, for example, is an electron acceptor, and so is oxygen. And you see those axes, the arrows show concentrations increase away from the origin to the outside of the radial diagram. And then manganese and iron, those are produced during biodegradation. They're byproducts. And those axes are in the opposite direction. So under aerobic conditions, they're low concentration. As they increase, concentrations move towards the origin. So what happens is because we have reversal of axis directions between electron acceptors, metabolic byproducts, we can really easily see aerobic conditions all plotted on the outside of the radial diagrams. Strongly anaerobic conditions are plotted on the inside. And the diagrams at the top just shows what you might see if you have biodegradation starting to occur as groundwater moves through a source area, where it transitions from aerobic to strongly anaerobic conditions. And the radial diagrams at the top, those are actually the same as the data in the table on the bottom, but as you can see, much easier to visualize with the diagrams than trying to look at the table. So that's another thing that you may find useful with PFAS sites or even chlorinated solvent sites, metal sites, hydrocarbon sites, etc. So what we've talked about are with PFAS site characterization, it's not just looking at one species at a time. We do have to do that, but we also have to look at how all these interspecies are related to each other, like parent versus daughter species, short versus long chain to tell us what remedies might work, what might not. Sulfonates versus carboxylates can be helpful for differentiating between sources. So sometimes one radial diagram map might actually replace 5 to 10 different chemical species maps. These radial diagrams can help you actually visualize attenuation along a flow path for a number of species. At the same time, we can look at a number of PFAS of concern and where they exceed. And as we showed, we can look at redox zone delineation as well. So I'm going to stop there and I'll just walk through a quick demonstration of the software to show you how it's set up, how we go through this process, and then we'll take questions after that. So Visual PFAS, so I just wanted to let everybody know if you want more information, you can just go to www.visualpfas.com. And WST's got a great website there with more information. So that's my cue. I'm going to switch to the software here. And so with the software, really what it's set up and intended to be is it can be an internal tool for consultants to look at data. I use this all the time for making presentations. I also use it sometimes for making final report figures, or sometimes I'll export the radial diagrams and stack bar maps to GIS or AutoCAD or Surfer if I want to make, add some more polish to the figures. So either of those options is fine. The first part of the software, we have to set up a base map. So you can see here with this base map, I've got a title. I can move it around just by double clicking on it. Optional scale bar, I can add coordinate axes if we want instead. At this particular demonstration, I'm going to show this is a hypothetical site, pretty similar to what we just saw. We've got 2 source areas, one where MW4 is located. That's going to have higher sulfonate concentrations and carboxylates as well. And then MW6 is almost all the FT-based product that was used for fire training. That's going to have mainly carboxylate concentrations. And we've got one upgradient background well, MW16. Groundwater is flowing from northwest to southeast. So we've got 2 different source areas with different signatures, and we've got some wells kind of in between that might have a bit of a mixture between those 2 signatures. So I'll just show you, like in terms of layers, the way this works. If I wanted to add a layer, I can add it, or if I wanted to edit, the line color, fill color, I'll just decrease the thickness of the runways, make it a little bit less obvious here. So these are easier to add layers, and these can be DXF files, shape files, or Surfer BLN files. And at this particular, with Visual PFAS, it's got a project database that it imports just from Excel CSV files. And one thing I like to do is I actually have location groups defined. So for example, let's say at this particular site, we've got 16 wells in total. Let's say there are 11 or 12 shallow wells. I can actually show the locations of different groups. So these are the deep wells, 4 deep wells. And I made a group I just called the background, just one well in that. So maybe at some sites you've got 3 or 4 background wells, which you can show separately if you want to. So I'll just show all locations. And then what I'm going to do is I'll switch now to the radial diagram portion here. Before I go over there, I'm just going to turn off the symbols, and I'm going to bring in some radial diagrams in a minute. But the way this works, and I'm actually right now have open radial diagram properties file for the shallow wells. And I've also got open stack bar map, and we'll go through and see what these look like. So the way the software works is I switch between the radial diagram legend here, and if I'll show you what it's like when we go back and add that to the base map. But in terms of radial diagram legends, the basics that we have to input, okay, how many axes, obviously. And then for each axis, if I wanted to change the PFOA axis, that's the current one that's highlighted in red, I could actually change that by coming in here and picking any chemical from the project database list. And I can change the axes. For example, I can type in, just make it 160. So I can change the axis angles or the chemicals represented in each axis. I'll just cancel out of here so I don't change that. And then in terms of series, you've got reference series, which are going to be the same for all the wells plotted on the map. So I've got a maximum reference series for based on all the wells at the site, and shallow concentrations are highest at this site. I've also got a separate reference series for wells in the deep zone. That's maximum of only the wells in the deep zone. And I've also got a reference series for background concentrations, which in this site is just MW16. And I've only got 2 events entered in the database here. You could have 10, 15 monitor events, and you could actually cycle through them if you wanted to, one at a time, and see how things change. And then in terms of locations, right now I've selected only the shallow wells. I could actually deselect that. I could say, let's not select the shallow. Now I'm looking at all the wells. I could turn them all on. But I actually don't want to do that. I actually just want to show the shallow wells for the site. And this filters, so if you have I've got some sites with hundreds of wells. So maybe you've got different areas with 20 to 30 wells in each area. You can group those and put them in the database as groups. And it just gives you a smaller list of wells to choose from. So here I can select shallow wells only, or I can select all the wells. So everything else is similar. So one thing to let you know with non-detects, those are represented in the database. And I have the option of plotting non-detects at the minimum range of each axis if I wanted to, or I can plot it at the detection limit, and it could be reporting limit or MDL, doesn't matter which you enter in the database. Or you can plot it at detection limit divided by 2. The default is just detection limit. And you can see in this particular well, there's a non-detect symbol shown. So for chemicals, let's say PFOA, I wanted it instead of log scale, maybe I want to make that an arithmetic scale. And when you change it, the database, that software knows what the ranges of concentrations are in the project database. So it automatically changes your axes. But let's say I change that back to log scale. I do find if things change by orders of magnitude, using the log scale axis can be really helpful. I can change the min and max ranges here. I can see what's actually in the database and make sure what we have is reasonable. In this case, I'm actually plotting the same min and max ranges for all chemicals. Just helps me to see which are high and which are low across the site. There's optional cleanup criteria, where you show exceedance symbols. Series, I can change the colors of series fill or lines. I can make the series fill transparent. Opacity means transparency, so you see the layers underneath more easily. I can turn non-detect symbols on or off, or exceedance symbols on or off. I tend not to show exceedance symbols for the reference series, just for the monitor event series. Okay, so let's go back to the base map, and then let's say now we want to add radial diagrams. So I've pre-made these radial diagrams, so I'm going to add just the shallow wells right now. So I'll open that. I think it's frozen. There we go. So now I've added them, but the diagrams look a bit small. Like one thing with radial diagrams is you want them to be as large on the map as you can make them. So we do have the option, like I could go back to the properties, I could go back to the map, and I could change the axis length and map units. But instead, I'm going to just do that on the base map because it's easier to just visualize it, change it while I'm actually looking at the base map. So I can click on that radial diagram and I can press the edit button. And the one thing you can edit with radial diagrams is the axis length, because that is a trial and error thing. You see what works best. So 1500 works pretty well. I've still got some space here. So I'm going to try and increase that a bit more, because the larger these are, the easier it is to count tick marks and changes in magnitude between wells and the reference series. So now we've got the radial diagrams plotted. Let's say I want to add now the deep wells. I can plot those separately actually on the map. So now I've got the deep wells. I'm actually, in this case, giving them a different color so I know which wells are deep. They actually have a different reference series because there are different maximum concentrations in the deep versus the shallow aquifer. Otherwise, everything else is the same. And I can change the colors of the labels so I know which are deep wells, which are shallow. Or if I want to plot, so let's say I wanted to And this is what I do a lot is I'll see something and I'll think, well, I want a thicker line or a different color. So I'm going to come into the shallow series, and let's say I'm going to change the color of the fill. And instead of the green, maybe I want to plot a light blue. Let's go with something like that. Going to make it a bit more transparent. I'm going to go back to the base map and just see how that looks. And then a lot of times with this, you just go back and forth between your properties and the base map to find really what works best. But it's pretty simple and pretty quick to do. So now let's say that I want to plot the background concentrations, just to show you another example. So this is really helpful, I think, when you have, let's say you've got an industrial site with maybe there are low PFAS concentrations, but a lot of industrial areas are going to have PFAS coming from upgradient sites. So definitely you want to plot your background wells and see how those compare. So I've actually got a reference background series, and that's based on the MW16 concentrations. And we can see in here the wells on the west side are similar, maybe even a little bit lower than background. So maybe those wells are not impacted by the site. These other wells, downgradient of the source area, much higher concentration. So obviously those are site impacted. So this is a nice simple way to look at plotting the reference series with a monitoring event. Really helps you to identify where you might have site impacts, especially at sites where PFAS is pretty low. Maybe you can show it's not distinguishable from background just by making a diagram like this. Okay, so let's turn off the radial diagrams, and now I'm just going to show you bar charts. These are actually easier, less inputs. So total number of locations, sorry. So similar to the radial diagrams, I can pick the locations pretty easily. Here I actually pick how many chemicals I want to show in the bars, and I've got 8 in total. And I'm picking from a list of carboxylates and sulfonates I'd previously defined. And then I pick the monitoring event. I'm going to pick the first one that's available. And then all I do is I create a line here for each of the intervals I want to show in the stack bar. I come in here and I define which chemical I actually want to show. And then I come in here and I pick the color. And I tend to reuse the same colors over and over again for different sites. Just once you find colors you like, it's hard to find colors that work. So keep using your colors when you like them. And that's about it for these. It's pretty straightforward. So I'm going to come back here. I'll turn on, now I'll just turn on the bar charts. And this shows what it looks like. So I can edit as well. I can click on that. I could edit the width and length of the bars. Maybe I want to make them a little bit narrower. Just apply that. So that's just a trial and error thing as well. Depends on how close your wells are to each other. And let's say one thing that's useful that we can do pretty quickly with radial diagrams and stack bars, sometimes your wells are really close together. So let's just say there's an example where I've got this MW8. Let's say there was another well close by. You've got to offset one of them, and we show an arrow pointing to the actual location. So let's say I want to offset location for MW8. So I'm going to come here and I'm going to say, I'm going to digitize this point. And when I press OK, it actually stores the coordinates in the clipboard. So then I'm going to come back here. I'm going to go to the bar charts. And if I go to the map tab, I can click which locations I want to offset. So I'm just going to click this. Right now, there's no locations offset. I'm going to double click on that MW8. And I'm going to enter the offset coordinates. So I'll click this MW8, highlight that as the current row, and I'm going to paste the digitized point coordinates I had just saved. And I'm going to apply that and press OK. I hope I picked the right well. Let's see. Yep, I did. So when you offset radial diagrams or stack bars, you have the option, it doesn't have to show up, of showing an arrow pointing to the actual location. You have an option to show the actual location symbol. Also, the symbols on the bars, sometimes you really want to make the point the bars are shown, coordinates for the locations are at the bottom of the bar, so you can show a symbol there, or I can come in here and I can actually turn that off. Let's say I come down here, I can turn off the bar location symbol, and now I come back here, and we no longer see that symbol at the bottom of the bar. But I still see the offset symbol. That was a different option. So that's it. So this is how we create the radial diagrams and stack bars, plot them on a map. You can then print this to a printer, to a PDF file, or you can save it as images if you like, and use them in PowerPoint presentations or report figures as much as you like. So I'm going to stop there and see if we have any questions.
Hey, Grant, that was a great presentation. It just shows the value of visualization, especially when you're dealing with so many parameters and the complexities around PFAS. We do have a question here from someone. Can we use Visual PFAS tools with other chemicals besides PFAS?
Yes, good question, because definitely this tool was actually made 25 years ago for chlorinated solvents to look for lines of evidence of monitored natural attenuation. So yeah, you can use we focus it on PFAS because there's an urgent need for that, but you can use the same tool for chlorinated solvents, hydrocarbons, metals, radionuclides, redox indicators. So definitely, and it's the same approach.
Perfect. Okay, and another question: what formats are available when exporting radial diagram maps, and can these be imported into AutoCAD or GIS for final figure polishing?
Yeah, so so you can export first. You can print to a printer or to a PDF file, and you're printing basically that one-page base map when you do. Or you can export electronically to Surfer BLN files or DXF files, which you can then use to import radial diagrams and stack bar maps into your figures that are either in AutoCAD or GIS. And the key thing is when the radial diagrams come in, they're not all one figure. You get each series is a different shapefile. The axes are a different shapefile. The symbols are different shapefiles. That way you can use different symbols in your final figures if you want, different line colors, thicknesses, etc. So there's a lot of flexibility if you want, because everybody's got different figure templates for the reports. We didn't want to try to recreate that. So you've got a lot of flexibility for bringing these into GIS or AutoCAD or Surfer to plot up your final report figures.